questions and discussions. Okay, please, Pierre, go ahead.
Thanks a lot, Julia, and thank you very much. So I'll discuss this work I've done in collaboration with Jonathan Luisoni and Gavin Salam about a year ago on assessing the impact of hadronization models and the extraction of a strong coupling constant with the C parameter. So as we know, current performance of collider experiments has been challenging our ability to carry out precise perturbative calculations for collider observables. But in a selected number of cases, this is not enough even. And non-perturbative corrections are already a bottleneck on the way to perform precise predictions for these observables. There are several examples at the LHC, such as the precise extraction of the W mass, for instance, from PT distributions of leptons in Drelian, as well as the extraction of the top quark mass that has required to deepen the understanding of certain aspects of QCD beyond perturbation theory. One of these observables, one of these quantities, is by definition the strong coupling constant, as is relevant for this workshop. That besides of course, the necessity of extracting one of the least precisely known standard parameters with high accuracy, this inaccuracy is also impacting severely the precision that we can reach in certain collider observables where actually accurate calculations are required. And so an example is the total cross-section for the production of a Higgs boson, where, as you can see in this table, the uncertainty in alpha S has a heavy impact by considering about half of the error budget. So improving on the current uncertainty shown in the world average is absolutely paramount for high luminosity as well as future collider applications. To make things a little more dramatic, if we look at the world average, as we know, this is made of, it combines several extractions from different measurements, and which feature a certain spread, cover a certain spread of values of alpha S. The largest spread is shown by this category, that is extractions from event shapes and jet rates in the plus and minus collisions. The clearest feature that sort of is treated differently across these extractions is that of hadronization models. In particular, while this set of high values of alpha S, more compatible with the world average, assess hadronization, the impact of hadronization with Monte Carlo generators, these three values here correspond to the extraction with event shapes like thrust and the C parameter, and the estimated hadronization with analytical models. So the smallest of these values is an extraction from the C parameter that I'll be focusing on today, and is a fit from Andrei Huang and collaborators. And this happens to be in mild tension with the flag average at about 3 sigma or so. So while, as we saw already in this workshop, there are excellent prospects from lattice QCD to reach very high precision in the coming years in the extraction of alpha S, as well as several techniques already being studied at future colliders. It is nevertheless important to understand the spread, and which requires a certain understanding of non-perturbative dynamics. First of all, to control the correct treatment of systematics in the combination of these fits, as well as to understand whether the reliability of current hadronization models in the context of other collider observables, of course. So there are essentially two ways to include the effect of hadronization in this type of alpha S extractions. The first one is through Monte Carlo models. This basically means build a migration matrix to connect parton level to hadron level using state-of-the-art Monte Carlo generators, and then apply this migration matrix to precise perturbative computations. Now, the pro of this approach is clearly that Monte Carlos have a realistic control over the kinematics of the event. These models are quite sophisticated. So, but the drawback is that they are tuned to experimental data using event generators with limited theoretical accuracy. What this means in practice is that the inaccuracy in the perturbative component is reflected in misestimate of non-perturbative corrections when the tuning is performed. So this is shown here, for instance, in this plot by a study of the moments of the thrust event shape. The two shades of blue show the perturbative component in the prediction for this observable, either with state-of-the-art perturbative calculation in light blue, as well as with Pythia in dark blue. And the two shades of orange essentially show the amount of non-perturbative corrections that are accounted for either with analytic models or with the non-perturbative model, the Monte Carlo itself. As you can see, the two are dramatically different in several cases. So improving on this is a very complicated question, and this very likely will require building more accurate Monte Carlo generators. So there is, however, a second approach, that is that of analytical models, which has the advantage that this can be immediately used consistently with state-of-the-art perturbative calculations. So there are many models, and there's a very rich literature, but the common denominator is that all these models are used to calculate the leading non-perturbative correction to a certain collider observable, say an event shape, in a power expansion in some kinematical variable. For instance, in the context of a plus and minus, this could be inverse powers of the center of mass energy of the collision. So observables like the C parameter, as well as all event shapes, feature a linear scaling in this 1/q expansion. So the leading power correction will be something of this type. Now, what I'll be considering here is one of these models that is known as the dispersive model, due to Docchiser, Marchesini, and Weber. And essentially, this model postulates the existence of a physical strong coupling constant that exists down to vanishingly small virtualities. And this essentially relies on a physical definition, on a physical scheme that defines the coupling as the intensity, the strength of soft radiation, of the radiation of a soft system with gluon quantum numbers. So this coupling is made of a perturbative and a non-perturbative component that in a schematic way is obtained by subtracting from the perturbative component, from the physical definition of the coupling, the perturbative component that is simply obtained by relating this physical scheme of the coupling to ms bar at perturbative scales. Okay, and now we know it precisely. So the way this dispersive model operates essentially is that you take your observable, the C parameter, and a leading power in this 1/q expansion. The non-perturbative correction essentially amounts to a shift in the value of the cumulative distribution, of the argument of the cumulative distribution. And to compute it, we need to calculate the shift in the C parameter value due to the emission of this soft system with gluonic quantum numbers, often called a gluer, which has a non-zero mass consistently with this dispersive representation, and that is used as a trigger of the non-perturbative scaling. Now, one subtlety is that this system at some point, of course, decays into massless partons, so the two gluons or a QQ bar pair. And this splitting correction, though, happens to be universal for broad classes of linear observables, such as the C parameter. And it just amounts to an overall correction factor that is known as the Milan factor. So what usually people have been doing is calculate this shift in the 2-jet limit, where the calculation is simplified by the kinematics of the event in that configuration, which essentially takes a very simple form that looks as follows. So the shift in the C parameter value due to the emission of this gluer is proportional to this alpha naught variable. That is the first moment of the physical coupling, defined down here on the right. This is a non-perturbative, by definition, non-perturbative quantity, and is extracted in the fit simultaneously with alpha S. then is proportional to this Milan factor that accounts for the splitting correction I just mentioned, as well as an overall constant, this zeta of C, that is observable dependent. And for the C parameter in the 2-jet limit can be calculated easily, and this is 3 pi. Then this mu I is just a factorization scale that essentially separates the perturbative regime from the non-perturbative regime in this physical coupling picture. And this can be varied, in fact, to assess the robustness of the whole framework. The second bit is just the subtraction of the perturbative piece of the coupling that I introduced before. Do you remember was the non-perturbative coupling that describes the emission of the glue, where it's just the difference between the physical coupling and the perturbative component. Now, this is all good, and this kind of technology has been applied for many, many years in a number of fits using best shapes as well as jet rates and more and slightly different variables. However, there is a subtlety that is what usually people do is to calculate this shift in the 2-jet limit where the kinematics is very simple, and then assume that this shift remains the same across the spectrum of the C parameter, and importantly in the region where alpha S is extracted. And specifically, what this assumes is that this zeta of C function is just a constant that is equal to 3 pi across the spectrum. Now, it is this is of course a question, and there's a question of whether this is a reliable approximation or not. And in this talk, as well as in the next talk by Paolo, we'll try to answer this question. Now, in the context of the dispersive model or any non-perturbative model, the 2-jet limit is quite special in that so calculating this shift in general requires some knowledge about non-perturbative dynamics of QCD, which in simple kinematical terms means when I radiate this gluer, I need to know how the rest of the event, the kinematics of the rest of the event is modified. But what gives me that information is essentially the matrix element for this configuration that, in other words, requires knowing a matrix element in some non-perturbative regime that, of course, right now I cannot access. Now, the 2-jet limit is special in that this recoil of the hard event against the emission due to the emission of the gluer essentially features a quadratic dependence in the kinematics of the hard partons, which essentially allows me to calculate the linear shift in the C parameter value without worrying about this effect at all. So I can just do a calculation in the soft limit, and I'm completely agnostic about how the hard event is modified by the emission of the gluer, and that is okay as long as I calculate only the linear correction. But as soon as I move away from this limit, I need to know how the hard event is modified, which is intrinsically a non-perturbative question. So how can we gain more information about this scaling across the spectrum? Well, the C parameter is special in that it has a second point across the spectrum that features a similar kinematical configuration. And this is essentially the 3-jet symmetric configuration where you have an emission gamma star, a Z boson decaying into a QQ bar and a gluon, all sharing the same energy. And this corresponds to C of 3/4. That is a point at which the C parameter distribution features a Sudakov shoulder. That is a consequence of the fact that the C parameter around that point depends only quadratically on the kinematics of the hard particles. This once again allows me to calculate precisely the leading power shift due to the emission of the gluer. And this calculation can be done again in the context of this dispersive model. And what we find is the expression here on the right that numerically happens to be about a factor of 2 smaller than the value that we find in the 2-jet limit. So now the question is, well, first of all, now I have this value of the non-perturbative shift at 2 points of the spectrum at 0 and 3/4. But in between, I'm not in a position to calculate anything because by definition there, I have a linear sensitivity to the recoil of the hard partons, and therefore I need some non-perturbative model to actually carry out the calculation. or an approximation of QCD in that regime. What I can do though is to parameterize the scaling between these 2 points by fixing the value in the 2 and the 3 jet limit. And this can be done by introducing this profile scaling for this zeta c variable. And so we try to sort of probe a broad set of functional scalings that that will give us an indication of how much these variations essentially impact the fit of alpha S. So using these different models, these different profiles, we fit alpha S using the C parameter distribution, using data from Aleph and Jade, using within a certain assumption for the experimental correlations between data points. And what we find is shown in the slide. So the plot on the left shows the different extractions of alpha S and the non-perturbative parameter alpha naught simultaneously. The little ellipses are the experimental uncertainties, and the shaded areas represent the theoretical error that are obtained with a conservative variation of all the scales and parameters in the theoretical prediction, essentially. What we see is that the different values of the different assumptions on the profile essentially span a range of values of alpha S that go from values of 0.112 with the standard assumption of a constant scaling across the spectrum, to values which go up to 0.116 or so with a very similar chi-squared, and we're now with a value that is compatible with the uncertainty with the world average. Now, this is clearly not conclusive because we don't know if one of these profiling scalings, if any, describes the actual correct physics in between. But the conclusion from an agnostic viewpoint is that the ambiguity or the uncertainty in our current modeling of non-perturbative corrections can in principle lead to a spread of the 3 to 4% level in the value of alpha S extracted with this strategy. So can we do more? One first step is to try and calculate this scaling in between. And as I said, what we need to know essentially is, at least the first approximation, is how the hard event kinematics is modified by the emission of the gluer. And this can be done by introducing physical recoil schemes that essentially absorb the recoil of the gluer among the other partners in the event. So in this case, we have a quark, anti-quark, and a gluon plus the gluer, and the quark, anti-quark, and gluon now recoil against the gluer according to some scheme. We take a sample of schemes that is inspired from technology developed in the context of higher order calculations or Parton shower generators. And 3 schemes have in common the fact that the local longitudinal, the longitudinal degrees of freedom are absorbed locally within each of the colored dipoles that are created by the Hart system of a quark, anti-quark, and a gluon. While the transverse recoil, so the transmomentum, is then absorbed either locally or globally across the full event. And one scheme, the so-called FHP scheme, is different in that the longitudinal recoil itself is now absorbed only partly locally within the dipole, and a component of it is assigned globally across the full event. So what we do is basically calculate the zeta of C profile using these recoil schemes. And unlike the previous case where we assume the scaling in between, this is actually a first principle calculation, though we relies on an assumption that is how the recoil of the gluer is absorbed within the rest of the event. So the results are quite interesting. And we see here that the 3 schemes that have a local recoil for the longitudinal component of the momentum all give the very similar, well, identical results. And these are the curves down here at the bottom of the plot. The FHP scheme, though, gives a scaling that is slightly closer to a linear scaling, and it differs substantially by the other 2. This gives us sort of confidence that the spread of schemes that the profiles that we assume in the fit gives a realistic idea of how much the extraction of alpha S is affected by this uncertainty. But we're not in a position, of course, to choose one of these schemes as the correct physical scaling. And this is something that really requires some non-perturbative considerations. Now, one very interesting development that happened more recently is the calculation of the scaling in the context of a large NF model, where essentially the QCD case of the emission of a quark, antiquark, and a gluon is extrapolated from the simpler QED case of a quark, antiquark, and a photon. Now, this Z of C function can be now obtained as a limiting behavior of by taking the linear term in the small mass limit of the gluer. And this is something that can be done fully exclusively. Now, this calculation finds agreement with what I've just shown in the 2-jet limit, of course, and in the 3-jet limit. But it also sheds light on the precise scaling across the spectrum. And in particular, they find that the classes of recoil scheme that are linear in the gluer's momentum in the soft limit all behave in a universal way, and essentially this explains why we were observing an identical behavior in certain families of recoil scheme, and at the same time sort of excludes the outlier in that plot that has a nonlinear behavior in the soft in the limit of soft gluer's momentum. So we'll hear more about this calculation in the next talk by Paolo. Now, so this is an interesting development, and certainly it would be nice to see how this impacts the phenomenology to the extraction of alpha S, but it's not the end of the story. And there's more to it that has to do with how, so far we consider the emission of a gluer from a final state of a quark, antiquark, and a gluon. But there's a question of how much this picture is modified by considering additional soft gluon radiation. And intuitively, this is simple to understand since, remember, the ambiguity was due to how the gluer modifies the momenta of the hard partons. Now, within a recoil scheme that sort of by now we more or less understand, the problem is that if you have a system with many more soft gluons, the way the recoil due to the gluer across the system, of course, leads to an effect that can be substantially different from what is predicted from considering just a single gluon. And this plot here shows, in fact, this difference. The red curve is obtained by running a parton shower with a very small value of coupling that sort of amounts to almost a fixed order calculation like the one that considers a quark, antiquark, and a gluon. And at the end, essentially, this considers an amount of soft radiation and then the emission of a gluer that is assumed to be the softest particle in the event. And the predictions obtained are in perfect agreement with the fixed order calculation that we performed before. Then the remaining lines, the blue, the orange, and the green, show instead the same calculation, though by allowing the shower to radiate an arbitrary amount of partons with different cutoff values for the resolution variable. But the important message that in the surrounding of the 3-jet limit, the Sudakov shoulder, this shower prediction leads to very different result from the fixed order calculation that precisely give us an idea of how much of the effect of all order soft gluon radiation there. So this is certainly not conclusive. Once again, it's just hinting at the fact that there is more physics to be understood, and it definitely requires more studies to be performed in the coming years. So briefly concluding, I discussed the case of non-perturbative correction to the C parameter distribution, and shown that the presence of a Sudakov shoulder in the spectrum allows us to calculate the leading non-perturbative shift at this point in the context of an arbitrary non-perturbative model. This correction happens to be numerically about a factor of 2 smaller than the one in the 2-jet limit. This difference could potentially affect extractions of alpha S at the 3 to 4% level. And the question remains of what is the scaling in between the 2-jet and the 3-jet limit. And this first answer to this question has been given more recently by a large NF calculation that shed precisely light on how the non-perturbative correction behaves, at least the leading non-perturbative correction behaves across the differential spectrum of this event shape. Now, this is certainly a first important step towards a better control over this hadronization effects, though there are many questions that are still raised to be answered before we actually carry out precision phenomenology. Certainly understand better this interplay with all orders of gluon radiation near the singular points, as well as understand whether the large NF model with gluon radiation produces identical results to what have been computed in the context of a QED-inspired model. And ultimately, of course, we need to assess, at least in a heuristic way, the impact of subleading non-perturbative corrections like 1/q², both a LEP and future FCC energies to understand if we can use this type of technology to extract alpha S with percent level uncertainties. Thanks a lot.
Thanks a lot. Thank you.
Thank you, Pierre, for this very interesting presentation. Do we have questions? Yes, one here.
Hi, Pierre. It was very interesting to listen to this talk. And in the end, I have just a question concerning the difficulties you would have to extract the coefficient somewhere between 2 and 3 jet configurations. So is my understanding correct that in principle, it should be possible if to do things just numerically?
So it's more than that. It's not just the calculation, the computational complexity. It's more a conceptual problem. So what you need to know is you need to know the matrix element for the radiation of a quark, antiquark, and a gluon, and for the radiation of a gluer of this system. The gluer being a non-perturbative object, so living at very low scales. And this matrix element is by definition a non-perturbative quantity. So we have no tools to calculate it in full QCD today. So we can only estimate it in some ways. And now this some ways is either do some assumptions, like for instance, work in the approximation of this gluer being very soft. So I give it a perturbative matrix element that is that of a soft gluon radiation. And just parameterize my uncertainty in the way the kinematics of this gluer is absorbed by the rest of the event. But this is just a very a rough approximation. It doesn't give me any control over the actual answer. It's just a way to see how much it can impact the result. A better way is what Paolo will describe now, that is work in a model where in large NF, you basically have no confinement, so you can actually do a calculation with perturbative methods of the scaling. And this is an exact calculation within that model. So the question then becomes how much that model tells you about QCD, but Paolo will tell us about this.
Okay, I believe there is a question by Andre Hoanga in Zoom.
Yeah, I have a question. So when I view the problem from an operator formulation point of view, I know that in the Dijkstad limit, this non-perturbative parameter is related to a vacuum matrix element of Wilson lines describing two collinear colored lines. But in the 3-jet configuration, you have 3 of them.
Yes.
My question is, from that point of view, let's assume that in the 3-jet limit, you also have some kind of 3 Wilson lines, which makes up a non-perturbative matrix element. I do not really know what the numerical size of this non-perturbative matrix element is. So how does this enter in your consideration of this model, this kind of degree of freedom?
Right. So I haven't. I mean, I don't have a precise answer to this question. A very good question. So my gut feeling would be that around the shoulder you have a subleading power factorization theorem that Wilson function is precisely what you just defined. So it's some expectation value of 3 Wilson lines, and then the non-perturbative correction that we are discussing is basically that expectation value in the non-perturbative below lambda QCD.
Yeah, but do your current maybe the question is like this: do your current model parametrization of this issue, do that intrinsically assume that these matrix elements are the same, because you're using the same parameter effectively over the whole spectrum, but you have this other function which is now becoming dependent on the spectrum?
So you're using the same alpha naught. So you're still working under the assumption that the radiation of the gluer is described by the same coupling constant in the non-perturbative region. Yes. Whether that is a so right now I don't see why that should be an unreasonable assumption, but yeah, maybe I should think about this a little more.
Perhaps can I perhaps add something that I think that the assumption is that when you have 3 Wilson lines, essentially you get the sum of a couple of Wilson lines of all the possibilities. So you get a QQ bar term, a QJ term, and Q bar G term. So I think this if you assume that the radiation comes from the sum of these 3, then everything goes back to having 2 Wilson lines. But of course, this is no one has written down an operator at the moment.
Yeah,
yeah. I mean, the reason why I'm saying is that if we would calculate it, of course, I have to split my hemispheres in a different way, basically the jet size. And this non-perturbative effect, in some sense, parameterizing the non-perturbative amount of basically shifting soft radiation between the 2 hemispheres and the dijet limit. And in the 3-jet limit, I'm not sure whether how equal it is.
I mean, Andrei, it is done in the frame of the dipole. So
yeah,
is it done in the frame of this radiating dipole?
So maybe I can. So what you're saying is basically how to split the hemisphere, meaning how to calculate the observable. That is something that is not ambiguous in the 3-jet limit.
No, this is
right.
Not what I meant. Yeah, no, but I don't think it's
the ambiguity of assigning now the gluer to an emitter and a spectator, that it precisely reflects this ambiguity in the recoil scheme. But this is an irrelevant. I mean, it is irrelevant a leading power 1/q in the 3-jet limit. Anywhere away from that point or away from the 2-jet limit, that becomes the important question, right? And that we don't know precisely what happens there.
Okay, so
can I ask a second question?
Maybe now or after the talk of Paolo? Shall we wait for the talk of Paolo and then, you tell me, is this really to Pierre, the question?
Yeah, I think it is, but
okay,
Paolo can answer it too. I can answer it also after Paolo, no problem.
No, okay, then ask it now if it's a question to Pierre and his slides, and then go ahead.
I should go ahead?
Yes, please.
Okay, now my question is, if you think about thrust, do you have any statements on thrust along the similar lines?
Right, so in what I've just shown, I cannot apply directly to thrust with any rigor, right? Except, of course, assuming the same set of recoil schemes and calculating and see what happens. And we'll find a similar spread of what I've shown for the C parameter. But you can do it in large NF, for instance. That doesn't require the existence of a point with quadratic scaling. So, and I can anticipate what happens is that the calculation that we perform by assuming these recoil schemes, these ones that are longitudinally local, agrees with what Paolo and collaborators obtained, in large NF. So, so within the dispersive model, what I just shown, that is not predictive for thrust, but the large NF calculations tell us more about that.
Okay.
We should move on now. Thank you very much.
Thanks.
Pierre. Thank you. Yeah. Please go ahead.
Okay, so let me say that we follow up on the talk by Pierre. Although this thing came out from a totally different line of research. So this was work done together with Fabrizio Caola, Silvia Ferrario Ravasio, Giovanni Matola, Kirill Melnikov, and also a student of Kirill, Eliaslan Ocelik, I think is the way to say it. So, okay, this is a quick outline, right? I will just review briefly what's the problem with the plus and minus shape variables. And I will describe this breakthrough in the calculation of linear power correction in the 3-jet region and discuss some application and prospects. So historically, the measurement of alpha S directly from the QQ-bar-G vertex in plus and minus annihilation has played a very important role in the historical development of QCD. So in practice, it is very convincing, since left, I think, it's very convincing at the 10% level. But if you want to use it for measurement of alpha storm, it is affected by uncertainties at a non-perturbative level. So perhaps it's not the best method to measure alpha storm, but it's probably the simplest context in which you can test perturbative application of QCD. So if you can control there the perturbative expansion and some power correction, you can think that you can transport this knowledge to collider physics. So the determinations quoted in the PDG here are from Monte Carlo models together with next-to leading calculation, next-to-leading log summation are more or less consistent with the world average within error. But as we saw in the talk by Pierre, there an approach that should be better, I mean, based upon analytic models, so not relying upon less clear models of hadronization using method like SCAT, dispersive models, and things like that, tend to give lower values and a bit in conflict with the world data, actually. So in the PDG, this criticism is mentioned, right? They say the systematics are not yet fully verified, and the more focused criticism comes from Lusoni, Monni, and Salam, where they essentially say that since you're extrapolating a result in the 2-jet region to the 3-jet region, there could be an error because of that. And they were able to compute non-perturbative effects for the parameter at the 3-jet symmetric point. They found a result which is twice as small as the one near the 2-jet symmetric point. So this, of course, as you have already seen, depending upon how you interpolate between the 2-jet and the 3-jet, you may or may not solve the problem of the discrepancy with respect to the world attention, if you want, with respect to the world data. I will not insist on this, you've just seen it. So the new development is the following, is that under assumptions similar to those that allow the computation of the non-perturbative corrections near the 2-jet limit, we can compute non-perturbative correction in the full 3-jet region. So we can compute this zeta function that parameterizes the non-perturbative correction as a function of C, not only for the C parameter, but also for thrust and for many other shape variables. And our result for the C parameter agrees with the lowest curves in the paper by Lusoni, Salam, and Monni. So it confirms that perhaps non-perturbative effects should be smaller than what they actually implemented now in this kind of fits. So, yeah, unfortunately, I don't know how to get rid of that. Is it possible? No. The stripe, they don't see it. Okay, very good. So, yeah, a bit. No, never mind. No, don't worry. Okay, so to explain how it is done, of course, this is a short talk. I cannot go through too many details, but let us first recall why we can compute the non-perturbative effect in the 2-jet limit. And so non-perturbative effects are associated with the emission of soft gluons with smaller shellness, so that the associated value of alpha fits the Landau pole in essence. So if you think about any shape variable observable, its expectation value is going to be the integral of the cross-section times the value of the shape variable due to the QQ bar emission in the 2Z case, plus a gluer, plus this small thing, right? So then you can rewrite it by subtracting and adding stuff. So you subtract from the cross-section, including the gluer, you subtract from the value of the shape variable, including the gluer, you subtract the value of the shape variables without the gluer, and then you add it back, right? But of course, the shape variables for a QQ bar pair without emissions is just a constant, right? It's just two back-to-back jets, the back parton, each of them with half the energy of the annihilation. So the shape variable goes out of this integral, and here you have a total cross-section. And the total cross-section is known not to have any linear power corrections by many different arguments, but the most powerful one is that there is no operator expansion that guarantees the correction is suppressed by 4 power of Q. So you're left with this, term. Now in this cross-section, the difference between the two value, the shape variables, with or without the gluer, suppress the region of soft moment of the gluer. Right? So they tend to 0. So this cross-section is finite. The sigma is divergent. The soft emissions is divergent, but this is actually finite. And the leading contribution in terms of the mass, or the energy, whatever you want to call it, of the gluer, is due to the most enhanced part of the cross-section, which is the soft one. So in essence, you can compute this just by taking the soft limit approximation of the cross-section. And that's why you can compute it, right? So this is for the 2Z case. Now, next, let us recall why Luisoni, Salam, and Monni can compute it in the 3Z case. So I repeat what Pierre said, but I think it's useful for what I have to say later. So they observe that for the C parameter, which is a bit special actually, near the 3Z symmetric limit, its expression is quadratic in the deviation of the momenta from the 3Z symmetric limit. It has no linear terms in here. So in a way, you can play the same game you did before, right? You take the C parameter with the gluer, right? And subtract it from the C parameter without the gluer. Sorry, this S should be C, but never mind. You subtract it and then you add it back. And again, in this integral is a bit more inclusive than this one. So you can argue that this doesn't have any linear correction. And this is more inclusive because this shape variable now is not very sensitive to variations in the momenta of the 3 parts that have been generated. So in a way, this is almost constant. So you can pull out a bit of sigma contributed by soft gluon, which is essentially inclusive. And so it doesn't have quadratic linear corrections. And you are in the same condition as before, right? This difference suppresses the cross-section, so you can only use a soft approximation, and you can get a result in this way. So what do we do? What have we found? Well, we found the following. So assume that you have a mapping from the QQ bar gluon plus a gluer to a QQ bar gluon configuration. I call the momenta P1, P2, P3 for the QQ bar gluon and K for the gluer, right? And there's a mapping within these and momenta without the gluer, essentially. Right? So a Born-like 3Z configuration. But we require that the mapping is linear in the momentum of the gluer for small momenta. So these momenta with the tilde, right, those that are without the gluer, are given by the momenta with the full event, plus a correction which is linear in K, up to terms which are quadratic in K. So under this assumption, we demonstrate there are some caveats I will tell you later on, which I actually did, but we demonstrate that the integral, the fixed underlying Born moment, if you want to call it this way, fixed P tilde, the integral of the cross-section times any function of the gluer momentum that is linear for small gluer momentum is free from linear non-perturbative corrections. This is what we were after when we started this work. Actually, we were interested not so much in shape variables, but to show that in certain collider observables, there are no linear power correction. Typically, we are interested mostly in the production of a Z high transverse momentum, but the result we found is quite general. I mean, it explains at the same time why the Drellian doesn't have linear correction, why the rapidity distribution of the Drellian doesn't have linear correction, but also it tells you something about shape variables. Shape variables do have linear corrections, but these, if this mapping is used in associating an underlying Born event with an event with radiation, this transformation does not induce any linear power correction. So what you can do, same as before, we write a shape variable as its value with a full system of particles with the glue and recoiling and everything. We take away the underlying Born value of the shape variable and we add it back. Right? So here, in this last integration, we have the value of the shape variables calculated fixed underlying Born momenta. And this first integral, right? P here is a function of P tilde, right? So this will be an integral in K at fixed P tilde, right? Plus an integral in the whole momentum. Being an integral in K at fixed P tilde doesn't have any linear correction. So this is different than the other two cases where it was just being inclusive was enough not to have linear correction. In this case, there is this property of these mappings as such that you don't get linear corrections. So you get back to have to compute this thing, and the same consideration that we did before apply. Like this suppresses the soft region, so you can use the soft approximation, and you can compute the thing. Okay, these are the results. And this is for the C parameter, right? And this is the result for the full Q bar G thing, right? We did the calculation, we'll go back to that. I'm going backward from the end to the beginning to what is the connection with the large NF. Anyhow, this is something that can be compared with the result of Bisoni, Monni, and Salam. So for example, we reproduce the value in the symmetric point that they obtain, reproduce the value of the two-jet limit. You must reproduce it because in the two-jet limit, the three-jet configuration, because of angular ordering, has the same non-perturbative correction as a PQ bar system. So you must use that too. And in between, we agree with the calculation that Bisoni, Monni, and Salam did for certain recoil schemes, right? And that was shown earlier by, Pierre. I think I have it here actually again, right? So this is what they got. I didn't put a curve on top of this because it's exactly on top of them actually, but there are a few considerations, right? So we agree exactly with the result for the Catani-Seymour dipole, pan-local and pan-global recoil, but disagree with this for sure. And I forgot the other Plesser and the other one I forget. Anyhow, disagree with FHP recoil. Right? So, but it is easy to check that this recoil, FHP, does not satisfy our linearity requirement. So, what we have demonstrated is that these linear corrections do not contribute only if the mapping from the underlying bond, which is the same thing as the recoil system, is linear for small Bluer momenta. And FHP does not have this feature. So we understand why it does not overlap with the other three. On the other hand, notice that FHP gives the correct answer for the symmetric limit, because in that limit, it's not important the recoil you use. In that limit, the recoil is irrelevant because the C parameter stays the same irrespective of the recoil. Okay, so not only we can do the C parameter at this point, because we don't need to have a point which is insensitive to recoil. You can do anything, and this is anything. There are a class of shape variables that we can do. This is the result from trust. Also here you see that in the mid region, right? So this is the two-jet result. In the mid region, the result is lower, not as much as for the C parameter, but still quite a bit lower than what you would expect if you extrapolated this thing just to be constant. So if I still have some time, 2 minutes, 3 minutes, thanks. Okay, so it was a bit to say, what is the anatomy of the calculation? Right? Well, a glue essentially is a soft gluon that is connected with an effective coupling, right? It's radiated according to the soft approximation, so it's just an integral of this form. This is the rapidity of the glue. And the strong coupling constant is evaluated at the KT, transverse momentum of the glue, because the virtuality of the gluon is known to be limited by the transverse momentum. So, and this was, in the mid-90s, was a big business, I don't know how to call it, but people got very excited about the possibility to compute power correction for large class of observables. So this simplified view was not actually correct, and I think Mike Seymour and myself showed that the splitting actually is important. You must account for it, but if you account for it, you get a more complicated thing. You get the cross section with the final state with two partons. Here you get the absolute value of the square of a coupling, but still, I mean, this thing, for example, is fully calculable with certain large NF models, for example, and the result as a form of an integral of a quantity, which depends upon the cross section, times an effective coupling, which in the large NF model is fully calculable, actually. So if the shape variable is such that you can split it, I mean, you can, the shape variable is a function of having radiated two partons, can be written as the sum of two shape variables with the radiation of a single parton. If it has a property like this, you can show that this formula actually can be become equivalent to the naive formula up to a factor that is a factor that nevertheless gets absorbed into the parameterization of the non-perturbative effects. So our calculation is fully rigorous only in a large NF model. And in a large NF model, we cannot have a gluon here because I mean, you could, but it's too complicated to insert bubbles also in this gluon. So we did it for a photon. And in this case, the thing is fully rigorous. Right? So, however, once we realize that for shape variables, what is relevant is the soft approximation for the gluer, then you can assume that, well, you know, as long as this is the soft approximation for a gluer radiated by a Q2 bar pair, you can assume that if this is a gluon, we'll have to add up this dipole radiating a soft gluer, or the dipole due to a gluon and a quark, or to a gluon and an anti-quark. So by following this procedure, I think, which is similar to what Bisoni, Salam, and Monni do, can get a result for QQ bar G. It would be interesting to see if really generalizing the large NF calculation and considering all this insertion, even in this line, you get still the same thing. But I'm pretty convinced that you do, because soft radiation of a hard gluon that you know, splits or whatever is still like it came from a single parton, essentially, because of coherence, because of angular ordering and all these things. But probably it'd be interesting to study in more detail. So, okay, so I'm finished. So again, I mean, this is the problem of determination of alpha in shape variable is still an interesting one, because it's the simplest high energy process when you actually do a sophisticated and application of perturbative QCD. You can think about power correction, you can study them under several perspectives. And it is a contest, yeah, said that is interesting because of that. And it'd be interesting also to see if extensions to jets and also to hadron colliders, in the case of hadron colliders, we can get some interesting information also in this direction by using this formalism.
Thank you, Paolo.
Thank you, Paolo, for this very interesting presentation. Do you have questions for Paolo? Yes, I see a hand. Simone, please.
Hi, Paolo. Very interesting. So I admit I'm not very familiar with the approach, but I have two questions. So the first one is actually if you can comment on this last point, which is the first thing that came to my mind. I mean, I don't know of any application to, say, jets at hadron colliders. And I was thinking that maybe the additional complication is also that there you have also underlying event, which you would need to treat in some way.
Okay, the first thing I was thinking is that jets in the plus and minus. Jet definitions and all these things, that's the first thing, right? And then try to go to hadron colliders, step by step. But the approach, I mean, showing the absence of linear corrections worked also for collider processes. So, for example, showed that you don't have any, at least in the large enough approximation, in processes like Z plus 1 jet, right? So having a recoiling jet may make you think that there is a linear correction due to the recoiling jet, but there is none, right? So I think this would be studied further, but there are perspectives to do. But the first thing is the plus and minus, I think.
Thanks. And so my second question is about this issue of the recoil and then the various studies that have been done. So you also had the plot that also Pierre showed. And I was curious now to understand, so where would the PTA that is used to derive non-perturbative corrections to extract alpha S lie in that curve? Exactly here. So do we know basically where the, yeah, I guess that would be PTA 6 or maybe something even older, but do we know where it would lie?
I think it is dangerous to think that you apply this to Didi Monte Carlo in the following sense, that the absence of linear correction that lead to this result is okay if the soft radiation is correct. I mean, this fact that you have the cancellation of linear terms in these particular variables is related to the fact that soft radiation is correct also in large angle. Monte Carlos typically don't have, I mean, they have problems in that region. Right? So it's a difficult question. You have to see the Monte Carlo, how is it treating the soft radiation? Now there are all these dipole things, but perhaps that's okay, right? And then if they treat soft radiation in a satisfactory way, you can argue that there are recoil schemes that would minimize or cancel this linear unwanted linear correction. So it's a question that can be asked. We don't have an answer at the moment, but it's not, I mean, it has to be examined with care, and I'm not ready to say anything at the moment, but it certainly can be examined with this perspective.
So sorry, just to make sure I understand. So you say if I were able to correct PTA to have the correct behavior for large angles, soft emission. Yeah, so then I could put some points on these plots with a meaningful and do a meaningful comparison.
Sort of. Okay.
Thanks. Yeah, no, but I sort of understand. Then I'll study.
Yeah. Okay.
Thank you.
Okay, I don't see any other question to Paolo, so thank you very much, Paolo, again. And we move to the next talk by Andrii.
Okay, so hello everyone, and today I will present some thoughts about determination of alpha S beyond the next to next leading order from a plus and minus hadrons data. Before that, of course, I would like to thank to our organizers and to the hospitality for ECT. It's just wonderful. And I hope to see you once again, maybe in some years. But now, let's go to the talk. Oh. First of all, this talk is actually not about going just to N3LO in alpha S and presenting some results that would be extremely precise and should enter the PDG. This talk is not about waiting for the data from FCCE and assuming that it will solve everything. And it's not about the finding the only right hadronization model and the quoting extremely small uncertainties and so on. I will try to keep this talk more general and just discuss the future of extraction of alpha S from the hadrons data. So a brief reminder for colleagues who are not that familiar with E plus and minus two hadrons extractions, how it works. First of all, we measure some cross sections of jets or event shapes, and those quantities were already presented by Paolo and Pierre. And basically those are scalars or just 4 vectors. And to do the measurements, we actually don't need a very good and precise reconstruction of anything else. So we don't need a good measurement of collision energy, and even some amount of initial and final state radiation would be fine. Then on the theory side, we use a fixed order, massless, typically PQCD matrix elements to produce some parton events with some vectors, and that is done with Monte Carlo techniques. And from those events, we calculate the same jets, even shapes observables, and the results can be presented in this form, in the simplified form, let's say. I omitted all the scale dependencies, and in the end, having predictions for some even shape observable means to have all the A, B, C, D coefficients. The predictions can be also obtained with other techniques, with transformation techniques, and also those approaches can be combined. And after the theory calculations, basically we should take into account the hadronization somehow, and that is the trickiest part. And that can be done with Monte Carlo event generators or analytical models, which were also presented in two previous talks. And the final point, we compare the hadronization corrected theory predictions to the data. This is kind of simple part. And here just statistics should be done correctly, and that's all. But basically just minimization with chi-square techniques is doing the job very well. And almost all the measurements in the last 2 decades followed exactly that approach. And here you see some summary. I split those in 3 groups. Some non-global fits, which use just some energies, central mass energies. The second group is a global fit, where a lot of different energy points were used, and used with analytic hadronization models. And the last group is a global fit with Monte Carlo analytic models. Basically, what one can see is that global fits and wide range of central mass energies means best precision and so on. However, a huge problem here is that there is a discrepancy between the analytic and Monte Carlo hadronization, and that should be clarified. So a point here is that hadronization should be understood. Before that, before speaking about what one can do about the better alpha determination precision, first of all, of course, we can think about getting more data, and perhaps FCC will be the answer. We can think about getting better theory, for instance, going to higher orders, going to combination of QCD feeds together with some QED corrections, mass effects, and to do better summation. Then, in principle, we could think about doing the data analysis better, but it's already good enough. And we could think about reduction of number of assumptions. And for this type of extraction, it's not the case. This is a very theoretically clean and absolutely almost assumption-free method, so also not the case. And in the end, hadronization effects. So from this list, because we don't have FCC right now, we stay basically with the question, how we will improve the alpha S with better theory and better hadronization model. And what is more important? That was a case study for this paper. It's clickable. But before going into the details on that paper, we should think what actually constitutes a better precision, what defines the precision of alpha S. So what we understand very good and what actually easy to do is the propagation of statistical uncertainties, propagations with multiple uncertainties, some uncertainties and systematic shifts because of theory assumptions, like assumption on how we are running our alpha S and what do we use for calculation. Not so well understood is, first of all, the missing of higher order corrections of perturbative theories. Of course, it's a work in progress, and sometimes this uncertainty is addressed with the so-called scale variation, but the underlying reason for that is actually missing higher orders. Then, of course, modeling of non-perturbative effects. Yes, it was already mentioned before many times. And the thing that was not mentioned before is a discrepancy between the results from different methods and different models. In the simplest case, that is a discrepancy between Monte Carlo hadronization models and analytic hadronization models. So, having that in mind, we can try to perform the following analysis. We can just take the state-of-the-art NNLO predictions from the colorful NNLO and try to fit some N3LO coefficients for those predictions from data. In this way, we will try to simulate N3, try to approximate N3LO perturbative calculations, and then apply everything what we know about mass corrections, analytic calculations of some coefficients. So all the state-of-the-art machinery we have for perturbative calculations, and pick the simplest case of some even-shaped observables. In this case, it's even-shaped averages, and have a look what will happen. We can try to use all the available data, and with all those information, we can try to look at, we can try to perform alpha S extraction analysis and check if different Monte Carlo models will give different results, and actually if N3LO coefficients estimated from data will be useful. So to do that, we need some Monte Carlo, we need some data. And as I said, we pick it up for this analysis study, all the data for the C and trust variables from many experiments in very wide range of center of mass energies. And we use the state-of-the-art Monte Carlo for hadronization. And in principle, we see that Monte Carlo kind of describes data starting from 30 GeV, and we have enough data points for the analysis. And the hadronization corrections are calculated in this way, just as a ratio of predictions at hadron level, Monte Carlo over Parton level. And for analytic hadronization models, for the first time, we extended the very well-known analytic models presented in the previous talk, mentioned in the previous talk, to the alpha cube. And then for the average values, we have a nice relation that basically those analytic models just shift the averages by some known amount. So with all that machinery in hand, we performed many fits. Quite simple fits, I would say, in terms of data manipulations, just minute chi-square fits. We performed in many configurations like N3LO, NNLO, different hadronization models with different modes of gluon radiation. And in principle, all the fits describes the data quite well. Just the control results for at NNLO. The results are quite reasonable, apart from quite small hadronization uncertainties in some cases, but that's actually the problem we're trying to address. And at N3LO, we can get some results. And results are not actually that bad. In terms of numerical precision, I would say that the numerical precision is mediocre. maybe 20 years ago, it would be state of the art, 20 years ago, not now. What we see, however, is that in principle, the method works and there is some consistency in the extracted D coefficients, so the N3LO coefficients, and that is good. However, the most important part is that the same pattern of discrepancy between analytic methods and Monte Carlo approach still is in place, which means that if we will go to higher orders, nothing will, there will be not that much of improvement because of hadronization. So conclusions from this analysis is that it is possible to go to N3LO extraction even right now, but will be such an extraction competitive in terms of precision? No. So that's why the paper was not called like extraction of N3LO. And will the extraction of N3LO calculations alone help to have competitive precision in the future? Even if we will have all the data from FCCE, it's unlikely. Will more data alone will help that? No. I think it will be unlikely. And the main problem is the hadronization. Hadronization modeling and discrepancy between the Monte Carlo and analytic approaches is a thing that should be addressed. And that is a way to do better study. Basically, understand hadronization. And in this context, I would say that we are indeed waiting for FCCE a little bit. And in a recent study, there was a discussion of perspectives of alpha S extraction at FCCE. And it was very interesting for me to read, and I completely agree to the authors that how much the authors dedicated and underlined the importance of the hadronization studies. And until the FCCE is in place, we have some time, and hadronization should be studied, should be improved. And also in that context, there are two proposals for alpha S studies at FCCE. The first one is just general perspectives of high precision alpha S at FCCE. And the second, I would like to advertise it a little bit. And that is a high precision alpha S determinations from future E plus E minus 2 hadrons data below that peak. And here is a proposal in on one page. Oh, okay. So the idea would be to take data at future E plus E minus colliders, also far below that peak, between 30 and 90 GeV in some dedicated runs. So basically to repeat the Petra and Tristan colliders, and that will help to deliver data that would enable highest precision of alpha S extraction and simultaneously enough data to understand the hadronization with a very good precision. That will cost nothing to the future FCCE, and that will cost also nothing in terms of data taking. And basically, just in a matter of days, one will be able to collect enough data that will supersede all the data taken at that energies to this point. And that data will be extremely beneficial for many other things, like heavy quark mass running and impact of electroweak fields and so on. And here, let me conclude. I would say that theory community did a great job in perturbative QCD on E plus E minus 2 hadrons, and there is quite little space for improvement, even if it's completely clear where that improvement can be done. As I said, mass effects, higher order corrections, combinations with QED. However, in the end, the result is that alpha S from E plus to E minus data without any improvements in hadronization right now looks like dead end or making, again, a compliment to our theoretician colleagues, it looks like a completed task because of great jobs that was done. And that will be true even there will be new data. However, if the hadronization will be understood very well, maybe without new data, maybe with new data, this method of alpha S extraction from even shapes and jet observables in plus and minus will get a new life, and because it's the most straightforward way to get alpha S. And I hope that exactly that will happen, because in the end, there is no way to avoid hadronization in the QCD studies, and then the understanding of hadronization should be improved in any case. It's just original part of, organic part of QCD. Thanks a lot.
Thank you, Andrii, for this interesting presentation. Do we have questions? Yes, I see a hand. Please, Klaus.
Yeah, thank you for this nice presentation. Could you please go to slide 13? So here you presented the results at next to leading order. Let's take the first two lines for Monte Carlo and an analytic model. You find the same discrepancies. But also, if you look at the uncertainties for the Monte Carlo model, you have a very small hadronization uncertainty. The experimental uncertainty is also very small. And for the analytic model, you just have an experimental uncertainty, which is a factor of 5 larger. Can you explain this?
Yes. Typically, for analysis like this, a great deal is to get very good chi-square over number degrees of freedom, and then if it's not the case, it's better to scale. And here we just put the kind of how it was without scaling, and there is a huge difference in the chi-square for both fits. But we haven't done anything to scale the results. We were just putting them as they are.
So some of the chi-squares tell you that the fit doesn't really work properly.
Yes.
Okay. And then
yeah, I mean, that is exactly what we are telling, that we don't know, we don't have a good hadronization models, and that's why our fits are not that good. We have discrepancies. If we would try to do a kind of the actual alpha S extraction analysis, we would try to do our best in terms of reweighting everything, do statistical manipulations, throwing out some points. But here we just upfront telling that, look, Monte Carlo doesn't work, analytical models, it doesn't work. We see discrepancies, and we are interested in the discrepancies.
Okay, and then to add on that, on the next slide, you have the N3LO results with alpha S values of 0.13 and 0.14, which is, let's say, unbelievable, right?
Yes.
So it tells you that this fit, that what you are fitting here is subject to effects which are not under control, right?
If to put that, yes, exactly. I mean, that's why it's more like a discussion and report on the state of the hadronization understanding, and it's not we don't propose those numbers to enter any kind of PDG averaging or anything else.
I understand that.
the aim here is just to show that Monte Carlo and analytic hadronization models give different results, and those results are not good, and we should do something about that.
But so the fit was done essentially assuming that you can fit D and alpha S.
Yes.
But okay, I mean, obviously this doesn't work. This,
you can do the fit, but the
because D is a number, you cannot fit it, right? No, I mean, this is a number, you have to compute it and then you can fit alpha. But I mean, it's not surprising, I think, that you get this.
Yes, I mean, if you do simultaneous fit, in principle, we can. But if that would be a single point, of course, it will not work.
In any case, we agree that more understanding is needed. Thank you.
We have other questions from, don't see other hands. We have questions here. Okay, no. So please go ahead, Simone.
Okay, thank you very much. So during Paolo's talk, the connection here in Genova dropped twice. So I hope I'll manage to give my talk. Thank you very much for the invitation. And today I'm gonna talk about essentially the same issues we've been discussed in the previous talks, but try to give a different angle. So try to see if grooming, which is a procedure that I'll describe in a moment, can help with this hadronization correction in the context of alpha X extraction with event shapes. So the outline of my talk is the following. I'll give a very brief introduction about event shape and extraction of the star coupling. And then I'll go through a detour talking about grooming, so a way of reducing non-perturbative corrections with techniques which have been developed for the LHC. Then I'll come back to see whether we can apply such techniques to plus and minus event shapes and discuss things that we understand and things we don't understand yet. And then I will finish my talk going back to the LHC and try to discuss a few things about possible extractions of the strong coupling using jet observers at the LHC. Okay, so my introduction is really one slide, which has been already shown several times this afternoon, and is the plot which summarizes the extraction of the strong coupling. And in particular, we want to focus, we're focusing on extraction of the strong couplings, thrust and the C parameter mostly, which we know are in slight tension with the word average. And in particular, one study that sort of trigger our work on this topic goes back to a very, very important paper, which is now 10 years old, where the distribution of the event-shaped thrust was computed for the first time to an astonishing precision and QLL matched to next to order and used to extract a strong coupling. And as was discussed before, this extraction is in slight tension with the word average. One thing which was discussed already is that a analytic model of non-perturbative correction was employed in this extraction, and similarly to the C parameter done by the same authors. And one of the features that this extraction have is that we have a significant correlation between the parameter that governs these non-perturbative corrections and the strong coupling. And so in order to understand whether the way of treating non-perturbative correction has to do with this tension of the strong coupling, I guess it's fair to say that we need to understand better non-perturbative correction. This was the topic of the previous talks, or the angle I'm going to take today is to see whether we can reduce non-perturbative correction, so to get something which relies more on perturbation theory and has less of so that hadronization correction have less of an impact. So how do we do so? Well, here starts my first detour. In the past decade, there's been a lot of development in the context of jet physics in proton-proton collisions. And in particular, there's been a lot of studies that aim to understand better the substructure of jets. The main aim for these studies has always been driven by searches for new physics, but actually by developing algorithms which go under the generic name of grooming and tagging, people have discovered that we can actually gain better control on QCD observables in the context of jet physics. And in particular, I'm going to focus on this class of algorithms, which are named groomers. And very generally speaking, what a groomer aims to do is to resolve the jet on a smaller scale. So try to identify what is the correct scale of the jet. And with respect to the scale, to groom away, so to eliminate in a safe way, radiation which is soft and larger. And so a grooming procedure is a procedure that allows us to clean up the jet by eliminating soft physics. The particular groomer I'm going to focus on today is called soft drop. And soft drop, as shown in the first figure on this slide, exploits the clustering history that we obtain if we recluster a jet with the Cambridge-Jack angle. So we have an angular order clustering history, and which we can parse backwards. And so we can go back into the we can walk back through the cluster history of the jet, and at each splitting we can ask whether this splitting has some intrinsic hardness, or whether we should consider this splitting as a splitting of a hard prong and something soft. And the detail of the way the algorithm works are not essential, but the take-home message is that this algorithm at every step checks whether the momentum balance between the two prongs is has some hardness, so it's symmetric and with some hardness. And the way it does that is through two parameters, which are external inputs of the algorithm, which are referred here as z-cut, which measure essentially momentum fraction, and the angular exponent beta, which essentially control what we mean with the large angle for the collinear element. So one of the reason I'm focusing on soft drop is that it's been shown to be what I would refer to as a theory-friendly groomer, namely that from his conception, which happened in 2013 at the Boost conference, it has seen a rapid development in our understanding of the way this groomer does. And so in 2016, for instance, the group at Harvard managed to prove a factorization theorem which involves soft drop jet masses or jet angularities. That means we can compute jet shape on soft drop jets, and they show that they can reach a resummation of very high accuracy, next to innovating accuracy. And actually, more recently, Andrew Lakrosky and collaborator even pushed this accuracy of the resummation to NQ the left, so the same resummation accuracy that one reaches with event shapes at the Hadron Collider. And there are many positive things about the perturbative structure of this distribution than one can learn. So, for instance, we have a better convergence of the perturbative series, and the reason we can reach such high accuracy is because nasty effects that usually hit us in jet physics, such as, for instance, non-global logs, are absent for this if you apply something. So this is all very well. We can calculate these observables to very high accuracy, but what about non-perturbative corrections? Now, the first thing you can think of is that I told you that the groomer aims to resolve the jet on a smaller scale, and so it goes without saying that the effective area of the groomed jet will be smaller than the effective area of the original jet. And so intuition tells you that the sensitivity of these observables to things like pileup and the underlying event will be reduced. And this is actually shown in this plot, where what we show here is the ratio of the hadron level with underlying event jet mass distribution divided by the same calculation but performed without the underlying event as a function of the jet mass. And you see that there's a very wide region of the mass distribution where this ratio is close to 1, meaning that the underlying event interactions are negligible in this range. Now, this is very interesting for jet mass distribution in PP collisions, but if you're interested into E plus E minus physics, the underlying event is no problem that we face. So what about hadronization corrections? These have, here we really have to do the calculation, because it's not guaranteed that the effect of grooming gives you free reduction of hadronization corrections. But actually you can look into this, and by exploiting models of non-perturbative correction, analytic models of non-perturbative corrections, as for instance done in this paper by Dasgupta, Mani, and Salam, you can realize that essentially there are two effects which are in play when you try and compute the hadronization correction to, say, the groomed jet mass distribution. So imagine you have a perturbative splitting, like the one in the figure, that gives you a value of the mass and of an effective radius. And then you try to see what is the effect of adding a non-perturbative emission onto this. Essentially very similar to what the contribution of the gluer, which was discussed previously. You can have two effects. First of all, you can have a shift of the jet mass in the same way that you had a shift of the thrust distribution before. And this will be proportional to the non-perturbative parameter, lambda, the PT of the jet, and this effective radius. But also here, the soft drop groomer, what essentially does, if you remember the definition of the algorithm, it checks balance or unbalance between prongs momentum, PT1 and PT2. And we know the hadronization correction can also give you a shift in the momentum. And the shift was calculated, the average shift was calculated again in the same paper, and it turns out to be negative and proportional to inverse powers of the effective radius. Now, while in a standard jet, the effective radius is the radius of the jet, here, because we are employing soft drop, the effective radius is given by the measurement, the point at which soft drop stops. And so you can do this simple, you can apply these simple analytical models of non-perturbative calculation, apply to a distribution to see how the perturbative distribution, the perturbative, say, 1/m distribution will be changed by non-perturbative correction. And that's what you find in the formula at the bottom of the slide. You see in red, I put the standard result, so what you will get for the normal jet mass, okay? And instead, if you also apply some drop, on top of this, you also have this m over pt to this power 2 over 2 plus beta contribution. And you see that this is a reduction of the non-perturbative correction. So indeed, and the two effects, the shift in mass and the shift in PT, actually have the same scaling behavior. Now, within this very simple model, we cannot compute the function f, which sits in front, but we can only have an idea of the power behavior of the non-perturbative correction, and we do see a reduction. So does this work in reality? So by reality, I mean a Monte Carlo simulation of hadronization corrections. So this is a more recent study that we did involving angularities, so in PP collision. And with these, I mean all non-perturbative correction that you get in proton-proton, so hadronization and the underlying event. So the two plots at the top are similar in spirit to what I've shown before. This is the beam by beam ratio of the hadron level with the underlying event contribution divided by parton level. On the left, it was the standard jet mass. On the right, for the groomed jet mass. And you see indeed that you have a reduction in the size of the non-perturbative correction, but also in the onset. So non-perturbative correction are pushed to smaller values. What we actually realized more recently, and this is shown in on the plots on the bottom, is that you can actually see these the advantage of grooming if you look at something a bit more complicated. So for instance, this we built this transfer matrix, which essentially tells you for a given value of the, allow you to say, to see migration effects. So for a given value of the observable at parton level, you can have a variety of values of the observable at hadron. And you see a feature which we didn't notice before, and is the fact that if you look carefully, the distribution on the right, which is the one with grooming, is very diagonal, more so than the one on the left, which is without grooming. So if you want, grooming also allows you to make this, to use an old language, this parton-hadron duality even more precise, because the corrections are really on the diagonal. Okay, so this was for the tour of grooming and soft drop technique for PP collision. So what we would like to do is to apply this technology to event shapes, and in particular to standard event shape, which is thrust. So as was discussed before in previous talks, I report the definition of the thrust event shape, and thrust event shape is such that in the two jet limits, the vector-vector limit, its value is close to 1. Now we would like to apply soft drop and define a soft drop version of thrust. Now this immediately becomes a little more baroque, because these observables, these algorithms were built for jets. While here, if we discuss event shape, we would like to avoid talking about introducing jets. But the best we could do was to essentially come up with an operational definition of what we mean by soft drop thrust. And essentially we do as follows. We divide the event, we compute the standard thrust axis, we divide the event into hemisphere, and we soft drop each hemisphere. And once you soft drop each hemisphere, you have less particles, and you can build your soft drop thrust distribution, which is the formula at the bottom of the slide. And you see, it's not pretty. It's way less pretty than the standard thrust is, and there are essentially two reasons. The first reason is that now you have two hemispheres, so you really need to consider to measure things with respect to axis, two different axes, and L and R, while before you only have the thrust axis. And then you also have to add this contribution, which essentially tells you something about the particles that you groomed away. You need these if you want to maintain ISC safety across all possible values of beta, in particular beta equals 0. Beta is the angular exponent of soft drop. Okay, but it's a viable definition. It's not pretty, but it's something that one can use. And in the plots later on, I'm always going to show the distribution for the variable tau, which is 1 minus thrust, which is essentially the one we theorists usually think of, because it has the same scaling property as the value. Okay, so a while ago now, we did a similar study as the one I showed earlier for PP collision, but for E plus E minus event shape, in particular for soft drop thrust. And you see that on these two plots show again the ratio of the distribution computed at hadron level divided beam by beam by the distribution computed at parton level. On the left is for standard thrust for 3 different Monte Carlos with their standard tunes. And on the right is with the soft drop thrust with beta equals 0 and z cut 0.1. Now the vertical line, sorry, the gray band corresponds to a certain like 10% effect, and the vertical line tells me when at which value of tau I hit this 10% size of the non-perturbable correction. And you see indeed that by applying soft drop, you push this region where non-perturbative correction are important to lower values of the observer. Okay, you go from something like what is that, like 0.008 to something which is more like 10 to the minus 2. Okay, so indeed soft drop works in reducing and pushing a non-perturbative correction to smaller values of tau. Later on, we did a mock fit of alpha S using Monte Carlo data, and we found the following results. And I guess what we were after were 2 things. First of all, whether by using soft drop thrust, whether we had a smaller dependence on the fitted value of alpha S on non-perturbative correction. This is supposed to be shown in the first plot. Now, you shouldn't pay too much attention on the value of alpha S that you get. These are not very sensible because we use a simple theory, the next within log plus the next within order, so we don't really have a control. We can't really get a good fit. And what we wanted to see is whether by using soft drop, the jump that we go from a fit which is only resummation, indicated by res, to the fit including non-perturbative correction, whether we see a smaller jump with soft drop than with standard thrust. Now, you can see in some points that this is the case, although the uncertainties are too large. And at the end of the day, this study was a little bit inconclusive in the sense that we seen the trend we were expecting. The fact that we were doing a fit with reduced accuracy didn't allow us to make any firm conclusions on this. A bit more interesting are the plots at the bottom, where we show the fitted value of alpha s as a function of the minimum value of tau, which was included in our fit, using the our analytic model for hadronization. And you see that indeed, if you push the value of tau min to very small, to be very small, the fit with plane thrust go completely crazy, it's not stable. While on the other hand, if you use soft drop thrust with, almost respectively all the parameters you pick, you tend to have a very stable fit down to smaller values of tau, so larger values of thrust, if you want. Okay, so I think this study convinced us that this is an interesting thing to look at. But I guess the question one should ask is, can we make it competitive? So if we think about standard thrust, this is the calculation by the MIT group and collaborators, we can think of like dividing this in the distribution into 3 different regions. So we have a very large values of tau. We have fixed order domain where we know the distribution, at least the next order, something more. Then you have a region where tau is much smaller than 1. You have to do resummation, and we know the resummation and cubed leading log. And then you go into a non-perturbative region where values of thrust are of the order of lambda divided by q. And here we have to either model our non-perturbative correction or use Monte Carlo. So soft drop modifies this picture in the following way. So we see, let's start with the good thing, so that the non-perturbative transition is pushed down. So this transition is pushed down, and the power corrections are also reduced, parametrically reduced. On the other hand, we'll see later, a richer structure of this region. We also have a resummation region which we control very well. So now we have more parameters. We also have these parameters that cut. So for us, the resummation region that we control very well will be for tau, values of tau much smaller than z cut, while the fixed order region leaves a tau of order 1. And you see now that because you inserted the new parameter in the game, z cut, then you can also have a region where tau is much less than 1, but of order of z cut. And here you see indeed that you have weird behavior, which I highlight here as almost as a point of not a cusp, but like an angular point in the distribution. And so the question is like, do we have to understand this region more carefully if we want to make our fit competitive? So let me say 2 words on these 2 new features. So one is the hadronization region. So there was 2 very nice papers by Andrii and collaborators and a subsequent one, where Andrii was not on, but similar set of people, that tried to examine the non-perturbative correction to soft drop mass distribution. And they did a very careful study using effective field theories, and they were able to identify 2 different regions. One, which essentially corresponds to the deep non-perturbative region, where you really need an understanding of shape functions to make any sort of statement, and another one when you can treat non-perturbative correction, well, non-perturbative effects as a correction, as a power correction, and they call this the soft drop non-perturbative, the soft drop operator expansion region. And I think what was interesting in their study, well, one of the few things that were interesting in their study is that first of all they confirmed the very simple model I discussed before with this mass shift and decay shift. But the formulas they developed was much more powerful. First of all, they were able to express the coefficient, the unknown coefficient that I wrote as an F before, in terms of 3 universal parameters, 3 for the quarks and 3 for the gluons. And they were able to understand how they depend on beta. And moreover, they were able to compute these coefficients, including resummation. So compute the Wilson coefficient including resummation. So to make the very simple analytical model actually something a bit more grounded in field theory. The other problematic region for soft thrust is this transition region which I mentioned. So the region where the value of the observable is of the order of z cut, but much less than 1. And here, I mean, people have been aware of this region for a while, but it was only really last year that Andrii Verbytskyi and students actually looked into that and tried to see whether one can make more firm prediction about this transition region. And actually, this is a very similar behavior as the one which was discussed by Pierre of the endpoint of the C parameter, because you have a sort of like cusp behavior. And Andrii Verbytskyi and students were able to write down a factorization theorem and perform a first resummation of this area. So a resummation where you don't assume the hierarchy observable much less than z cut, but the observable is kept of the same order of z cut. And in the plot, you see that this actually can be a big effect. So if you look at the plot of the distribution, you go from a behavior where you can really see the cusp to something which is smoother, but significantly different. And the resummation at the moment is not known to very high accuracy in this region, and so you have a large spread of prediction. And of course, if you want to include this region in the fit, then you probably need to control it better. Alternatively, you can try to leave this region out and concentrate on the tau much less than z cut region. But this is really up to really is for discussion. So message of the story is that we're building all the ingredients that are needed to perform, to have a precision prediction of soft drop event shapes, but we're not quite yet. We quite there. We have probably have all the ingredients, but we still don't know. We still haven't put them all together. This is all very well, you can say, but how can we test these things on data? I mean, grooming didn't exist when lab was active, and so there are no data on with grooming. Minus data with grooming. Of course, we can wait for the next collider, but also another thing which I would like to advertise that people start doing, and I think we should be interested if more people work on that. Lab data are available can be accessed by the collaborations, and so there will be a few papers in the past year, in the past few years, try to go back to data collected in the 90s or 2000 by different collaboration, Opel and Aleph, and I know of some effort in Delft as well, to try and go back to this data and reanalyze them using this more modern grooming technique. So for instance, there was a paper by Stefan Gluth and a collaborator on measuring things with the anti-AKT, or the effort driven by Jesse Taylor at MIT and many collaborators measuring energy correlation variables with RF data. And I think by doing this type of studies, I think this could be a good motivation, not only for extraction of alpha-S, but also for possible motivating future, these studies at future colliders. Okay, in the very final part of my talk, I would like to go back to colliders that we have at the moment. So back to proton-proton, and try to see whether we can use substructure variables, jet observables, to probe the strong cut and to what accuracy. So for instance, there was an interesting study, although they didn't look directly into extracting alpha-S, but they sort of showed that you can gain precision by using grooming and event shapes. Now, event shapes are typically not studied so much at hadron colliders because they are very sensitive to non-perturbative corrections like hadronization, but also the underlying event. So for instance, if you take transverse thrust and then you look at the plot on the left, again, this is a plot of this observable measured at pattern level, PL, or adding the underlying event and hadronization correction. And you see that really the big effect, the big distortion of the spectrum is due to the underlying event. And now you can apply grooming, and in particular, this is soft drop, Z cut 0.1 and beta equals 1, and you can achieve a distribution which is much more stable against these effects. And we know how to resound these observables at least to next to the log, and perhaps even a high accuracy. So this is something that could be interesting to look at. If we instead focus on alpha S, there was a study a few years ago now at Les Houches, which people explored the possibility of extracting alpha S looking at jet angularities or closely related energy correlation factors. And there was a study done both from the study tried to address both theoretical limitation and experimental limitation in terms of the resolution achievable with the knowledge at that point. Now, this was 2017, so maybe these plots need to be a little bit updated. I guess from the phenomenological side, not commenting too much on the experimental one, the biggest issue that was found was a very, very strong correlation, unsurprising, between alpha S and the core gluon fraction. Now, at the LHC, you can produce quark jets or gluon jets. We can discuss what this means, but essentially jets initiated by quarks or gluons. And you see in this plot that the gluon fraction and the value of alpha S are very, very strongly correlated. And so it's very difficult to then achieve something which is sensible for alpha S. Well, it's very difficult to disentangle these two effects. Of course, you would like to find something where the value of alpha S that you fit is somehow decorrelated from the gluon fraction. Now, this study there's an ongoing study to try and address these in a little bit more detail. This is work in progress by Ofi and Adi Patak, Mashworth, and Institute. So I should thank Adi for providing these results. And what they're trying to do, what they are doing, is essentially try to see how different effects, we discussed, quantitatively affect an extraction of the strong coupling using the jet mass or a jet angularity in proton-proton collision. So you see, if you look at the first plot, what they try to do is that they vary the 6 non-perturbative parameters that I mentioned before that they use to describe the non-perturbative corrections to subdrop, and the uncertainty, the resulting uncertainty on alpha S is actually of the order of a few %, so not too big. If you also include variation theory of the theory uncertainty, so variation of the next to leading log decimation, you arrive at 5% sensitivity. But the biggest effect that they find is really if they allow for a mixture of quark and gluon jets, and they allow to fluctuate this mixture by 10%. And they see this in the last plot that you get the uncertainty on alpha S jumps to order 10%. Again, I don't think we should get we shouldn't take this is still unpublished results, so we shouldn't take the values as finals, but this gives you a trend. This really the biggest issue is to try and see, well, the biggest contribution to the uncertainty really comes from this mixture of quarks and gluons. And so this brings me to the question, which is, can we find a way to break this degeneracy? So if you want to make this type of
Simone, you're really a bit out of time now.
I'm done. Okay. So you really need to find better observers to break this degeneracy, and if you still have this sensitivity to gluon fraction, then you probably also should worry about PDFs. So I apologize for talking too much. So these are my my conclusions, which I can leave here, and I'm happy to take questions.
Okay, wonderful. Thank you very much, Simone. It was a very interesting presentation. Do we have questions to Simone? Yes, there is a question here. Just a second.
Thanks. Hi, Simone. Thanks for the nice talk. I have two questions. So one on like what you showed on slide 11, I think. Wouldn't you very naively expect the non-perturbative corrections for beta equals 0 are larger than beta equals 1? While this plot is showing the opposite? Why is that?
The correction for beta equals 0 are larger. Well, I mean, so I think it depends on the observable. So if you take these, I would say for observable like the jet mass, no, I would expect them to be smaller. Although if you then look something more inclusive, then beta equals 0 becomes a problem because of some, like not everything will be IRC safe.
Okay.
So if you take beta, as you increase beta, you go towards the ungroomed case. So you can think that the ungroomed case has beta to infinity. Yes. So for a lower beta for this type of distribution, you should get smaller type of distribution like thrust of the mass, smaller effects. Okay. With the caveat that if you still want to look at the PT, then beta equals 0 will give you IRC unsafety. So your correction will be all over.
Yes. Okay, and so second question is, how do you define the soft drop transverse thrust?
I was not involved in this. So I'd have to look into it. So precisely mean, I think they still use, okay, I need to check it. I wasn't involved in this study. So I don't remember. I don't know if they define like hemispheres, but no, this is a +9. It's not a +9. Yeah. I don't know. I have to look it up.
Never mind. Yes, there is another question here. Just a second.
Yeah, just a very small remark on this slide number 10. When you show, when you show the regions where you have this much better improvement and much better control over non-perturbative correction, it would make sense actually to show what is a fraction of cross-section is in that region and not the region itself, because it's just region is just a region, it doesn't tell much. And it makes sense to compare the cross-sections.
Sure, I agree with you. I mean, there is a lot, yeah.
And do you know what is a fraction in lies in that region where you have the improvement?
So we checked this, was asked by the referee. So I don't remember the number, but we had like, this is the bulk of the distribution. So we have like almost all the cross sections there. I don't remember the exact fraction. But the referee asked us precisely this question. So we checked. But I don't think this is a problem. I mean, this is really the bulk of the distribution, so you don't lose much.
Okay, I don't see any other question to Simone. So thank you very much again, Simone. And please go ahead. Thank you, Alexander.
Excellent. Thank you. So good afternoon. First of all, I would like to thank the organizers of this workshop for the given opportunity to present a talk. The main subject of this talk is the calculation of the R ratio of electron-positron annihilation into hadrons from the hadronic vacuum polarization function within various methods and their implications for the determination of the strong running coupling. This talk summarizes the results of our studies over the past few years and presents some new results recently obtained in this field. Well, in general, the hadronic vacuum polarization function plays a central role in various decisive tests of the self-consistency of quantum chromodynamics and entire standard model that, in turn, puts strong limits on a possible new physics beyond the latter. In particular, the theoretical description of such processes as the electron-positron annihilation into hadrons and the inclusive tau-lepton hadronic decay, as well as the hadronic contributions to such precise electroweak observables as the muon anomalous magnetic moment and the running of the electromagnetic coupling, is inherently based on this function. Additionally, the energy scales relevant to all these strong interaction processes span from the infrared to ultraviolet domains, so that their theoretical analysis constitutes a native framework for a profound study of both perturbative and intrinsically non-perturbative aspects of hadron dynamics. Well, the hadronic vacuum polarization function naturally appears in the theoretical description of the process of the can be represented in the following form, where S is the center of mass energy squared, which belongs to the time-like domain, and L menu and delta menu stand for the leptonic and hadronic tensors, respectively. Gamma denotes the hadronic final state, and J is the electromagnetic arc current. It is worthwhile to emphasize from the very beginning that there is kinematic restriction to the hadronic tensor. Namely, this function assumes non-zero values only for the energies exceeding the hadronic production threshold, since otherwise no hadron state gamma could be excited. In what follows, small m denotes the total mass of the lightest allowed hadronic final state. Well, the hadronic tensor is proportional to the discontinuity of this function across the physical cut, and the aforementioned kinematic restriction implies that its scalar part, the so-called hadronic vacuum polarization function, possesses the only cut along the positive semi-axis of real Q squared starting at the hadronic production threshold. Once the location of the cut of this function in the complex Q squared plane is known, one can write down the corresponding dispersion relation. Bearing in mind the asymptotic ultraviolet behavior of the hadronic vacuum polarization function, it is convenient to employ here the once subtracted Cauchy integral formula, which is usually represented in the following form. Here, delta pi is the subtracted hadronic with a so-called R ratio of the electron-positron annihilation into hadrons. Well, for the practical purposes, it proves to be convenient to employ the so-called Adler function, which is defined as the logarithmic derivative of the hadronic vacuum polarization function, and therefore it doesn't depend on the choice of the subtraction point in the aforementioned dispersion relation. Here we deal with the space-like values of the kinematic variable. Basically, the Adler function plays a valuable role for the congruous analysis of the space-like and time-like experimental data. In particular, since the perturbation theory and the renormalization group method are not applicable directly to the study of the observables depending on the time-like kinematic variable, for the self-consistent description of the latter, one first has to relate the time-like experimental data with the space-like theoretical results. Here, the required link between the experimentally measurable R ratio and theoretically computable Adler function is provided by the dispersion relation, which immediately follows from the one shown on the previous page. At the same time, the inverse relations, which express the R ratio and the hadronic vacuum polarization function in terms of the Adler function, have the following form. And in this equation, the integration contour lies in the region of the analyticity of the integrand. So the last two pages present the complete set of dispersion relations, which express the functions on hand in terms of each other. And these relations will be our primary tool in what follows. And note that from now on, the massless limit is assumed. Well, prior to going into the details of calculation of the R ratio, it is worthwhile to say a few words on the QCD running coupling, which being the measure of strength of the strong interaction between colored objects, plays a fundamental role in the elementary particle physics. So the QCD coupling satisfies the renormalization group equation of the following form, where mu is the renormalization scale and small a denotes the so-called QCD couplant, which differs from the strong coupling by this factor. In the framework of perturbation theory, the beta function appearing on the right-hand side of this equation can be represented as the power of series in the strong coupling, and the corresponding expansion coefficients are currently available up to the 5-loop level. In what follows, for all of the higher order scheme-dependent perturbative coefficients, the MS bar subtraction scheme is assumed. Well, the solution to this equation can be represented as the double sum of the following form, where Q squared denotes the space-like kinematic variable, lambda denotes the QCD scale parameter, and small b is the combination of the beta function and perturbative expansion coefficients. At the one-loop level, the strong running coupling and the corresponding couplant assume a quite simple form. However, it suffers from the infinite non-physical singularity, namely the host pole and the inclusion of the higher loop perturbative corrections doesn't resolve this issue. The comprehensive reviews of this topic can be found in particular in these two works. So let us now recall briefly what the perturbative approach to QCD can say about the hadronic vacuum polarization function. Well, in the framework of perturbation theory, the latter can be represented in the following form, where small q stands for the space-like kinematic variable, mu is the renormalization scale, and small a denotes the aforementioned QCD color plot. Note that this color flavor prefactor is omitted throughout unless otherwise explicitly specified. In particular, at one loop level, the calculation of the respective diagrams results in the following expression, and it is worthwhile to mention also that the hadronic vacuum polarization function satisfies the inhomogeneous renormalization group equation, which actually binds together the higher order perturbative expansion coefficients appearing in this equation. At the first few loop levels, such renormalization group relations can be found in these works, and we shall come back again to this issue in a moment. Well, as mentioned earlier, in practice, it is convenient to deal with the Adler function, which is defined as the logarithmic derivative of the hadronic vacuum polarization function. So the corresponding perturbative expression and the homogeneous renormalization group equation immediately follow from the ones shown on the previous page. Similarly to the latter case, the renormalization group equation enables one to express the higher order perturbative coefficients entering this equation in terms of the lower order ones. In particular, at the first few loop levels, such relations have been known in the literature for a while, and the explicit form of the renormalization group equation which expresses the higher order hadronic vacuum polarization function perturbative expansion coefficients in terms of the lower order ones has recently been obtained at an arbitrary loop level. So this page presents the compact recurrent form of such relations, and the first two lines reproduce all the renormalization group relations coming from the homogeneous equation for the Adler function, and in order to reproduce the equivalent relations coming from the inhomogeneous equation for the hadronic vacuum polarization function, they have to be supplemented by the relations given in the third line on this page. So the obtained renormalization group relations for the higher order hadronic vacuum polarization function and expansion coefficients can also be represented in the unfolded explicit form. Basically, the obtained results can also be employed as an independent cross-check of the perturbative calculations, as well as in the studies of the renormalization scale setting in the theoretical expressions for the relevant physical observables, and all the details can be found in this paper. Well, for a general choice of the renormalization scale, all the higher order perturbative expansion coefficients contribute to the resulting expression for the Adler function. At the same time, the native choice of the renormalization scale leads to the well-known form of the Adler function, and the corresponding perturbative expansion coefficients are currently available up to the 4-loop level, and there are also some numerical estimations of the uncalculated yet 5-loop coefficients. So at the 1-loop level, the perturbative expression for the Adler function assumes a quite simple form, which, however, suffers from the low energy and physical singularity. There is a bit tricky way to eliminate the dependence on the renormalization scale in the expression for the hadronic vacuum polarization function, since the latter is not the renorm invariant quantity. The proper way of doing that was described a long time ago in the brilliant papers by Michael Pennington, and so here one starts from the perturbative expression for the hadronic vacuum polarization function, then calculates the Adler function, which is the renorm invariant quantity, then sets up the renormalization scale that factually amounts to the proper renormalization group summation in the space-like domain, and then calculates the corresponding expression for the hadronic vacuum polarization function by making use of the aforementioned inverse relation between these two quantities. In particular, at the 1-loop level, this prescription results in the following well-known expression for the hadronic vacuum polarization function, which also contain low energy and physical singularities. As for the higher loop levels, the explicit expression for the perturbative hadronic vacuum polarization function with properly eliminated dependence on the renormalization scale has recently been obtained at an arbitrary loop level, and all the relevant details can be found in this paper. So let us proceed now to the calculation of the R ratio of electron-positron annihilation into hadrons from the hadronic vacuum polarization function. The first method is quite straightforward. Namely, one starts here from the perturbative expression for the hadronic vacuum polarization function, then calculates the Adler function, then performs the renormalization group summation in the space-like domain, and only then calculates the corresponding expression for the R issue by making use of the aforementioned dispersion relation. The use of the displayed integration contour in the latter eventually results in the following expression for the R issue, where the corresponding spectral function is the discontinuity of the strong correction to the Adler function across the physical cut. Well, at the one loop level, the realization of the first method is quite simple. Specifically, as mentioned earlier, the one loop strong correction to the Adler function has the following form, and its discontinuity across the physical cut is written here. The integration of this spectral function can be performed explicitly. That eventually results in the following well-known expression for the R ratio at the one loop level. It is worthwhile to note here that the one loop time-like effective coplant has first appeared in this work and only afterwards was derived in these papers. So at the higher loop levels, for the illustrative purposes, it is somewhat convenient to keep the contributions of the different powers of the respective coplant to the spectral function separately from each other. That eventually casts the foregoing representation for the R ratio into the following form. At the first few loop levels, the spectral function can be calculated explicitly, let's say by hands, whereas at the higher loop levels, it becomes rather cumbrous and its direct calculation entails certain difficulties. Nonetheless, the explicit expression for the perturbative spectral function has recently been obtained at an arbitrary loop level that makes the higher loop calculations of the R ratio easily accessible. Here, the basic idea was to unfold this equation, then to calculate and represent it in terms of the most general form appearing in this equation, then to calculate the discontinuity of that general form across the cut, and then to fold it back again. That eventually leads to the following result. The rest of the obtained result is given on this page, whereas all the relevant details can be found in this paper also. As an example, the plots of the perturbative spectral function up to the 5 loop level are displayed in this figure. As one can infer, the spectral function appears to be remarkably stable with respect to the high loop corrections that in turn eventually leads to an enhanced high loop stability of the resulting expression for the R ratio at moderate and low energies. Thus, as mentioned earlier, the R ratio within the first method can be calculated as an integral of the obtained spectral function, and the respective integration can easily be performed by making use of the standard numerical methods. Let us turn now to the second method. Well, the things are actually even better here. Specifically, one starts from the perturbative expression for the hadronic vacuum polarization function, then calculates the Adler function, then performs the renormalization group summation in the space-like domain, then calculates the corresponding expression for the hadronic vacuum polarization function with properly eliminated dependence on the renormalization scale, and only then calculates, continues it into the time-like domain by making use of the respective dispersion relation. The earlier presented results actually make it possible to obtain the explicit expression for the R ratio, which is valid at an arbitrary loop level and therefore can easily be employed in practical applications. Specifically, the obtained explicit expression for the R ratio, which properly accounts for all the effects due to continuation of the space-like perturbative results into the time-like domain, is given on this page, and all the relevant details can be found in these two papers. Well, as for the third method, one first continues the perturbative expression for the hadronic vacuum polarization function into the time-like domain by making use of the corresponding dispersion relation, and only afterwards sets up the renormalization scale that eventually yields the commonly employed approximation of the R ratio. However, as argued in detail in these works, the renormalization scale set and used here actually amounts to an incomplete renormalization group summation in the time-like domain. In other words, as it will be discussed in a moment, in this expression for the R ratio, the effects due to continuation of the space-like theoretical results into the time-like domain appear to be only partially accounted for by the corresponding coefficients specified here. As for these coefficients, which incorporate the so-called pi-square terms, so they have been extensively studied over the past decades. In particular, at the first few loop levels, they have been presented in these works. And the explicit expression for the coefficients which embody the pi-squared terms retained in a commonly employed approximation for the R ratio has recently been obtained in this paper, and it is given up here. Well, so the time is tight, so I shall make a few notes on the aforementioned methods of calculation of the R ratio without going into the technical details, which can all be found in these papers given here. So it was shown that the first and the second methods yield the same result for the R ratio of the electron-positron annihilation into hadrons. The array expansion of the obtained expression for the R ratio at high energies takes the following form, and its validity range is strictly limited to the specified energy interval. This ray expansion implies that the contribution of a given order to the left-hand side of this equation appears to be redistributed over the higher order terms on its right-hand side. Basically, this ray expansion can provide a rather accurate approximation of the R ratio within the specified energy interval, but only if the number of retained pi-squared terms on its right-hand side is large enough. However, one usually truncates this ray expansion at the given order, thereby neglecting all the higher order pi-squared terms, though the latter may not necessarily be negligible at all. And it was also shown that such truncation reproduces the result of the third method for the R ratio. So let us address now the pi-squared terms which are retained in a commonly employed approximation for the R ratio. As it will be shown on the next few pages, the values of the coefficients which embody such terms significantly exceed the values of the Adler function perturbative expansion coefficients, thereby constituting a dominant contribution to the corresponding R ratio coefficients. Additionally, the coefficients which incorporate the retained pi-squared terms rapidly increase at the higher orders. That amplifies the higher order terms in the commonly employed approximation for the R ratio, thereby making its loop convergence worse than that of its proper form. Specifically, as one can infer from this table, the available Adler function perturbative expansion coefficients basically assume the values of the order of unity. At the same time, the coefficients which embody the retained pi-squared terms may assume rather large values, and some of them even exceed the corresponding Adler function coefficients by an order of magnitude. Eventually, this results in the following R ratio perturbative expansion coefficients, which turn out to be substantially amplified and sometimes even sign reversed with respect to the original ones. And as one can infer from this table, the relative weight of the pi-squared terms in the R ratio perturbative expansion coefficients actually varies from roughly 60 to 90% and even more. Well, let us address now the effects of the pi-squared terms which are omitted in the commonly employed approximation for the R ratio. As noted earlier, such approximation actually constitutes the truncated ray expansion of its proper form, and the validity range of such approximation is strictly limited to this energy interval, and it only partially accounts for the effects due to continuation of the space-like perturbative results into the channel domain. The contribution of a given order to the proper expression for the R ratio is redistributed over the higher order terms in its approximate form, thereby substantially amplifying them. In turn, this makes the loop convergence of a commonly employed approximation of the R ratio worse than that of its proper form, and increases the resulting uncertainty of the strong coupling and the QCD scale parameter associated with the disregarded higher perturbative corrections. In particular, as one can infer from this figure, beyond the two-loop level, the curves corresponding to the proper expression for the R ratio, which are displayed by the solid curves, are nearly indistinguishable from each other, whereas the curves corresponding to its approximate form, which are shown by the dashed curve, started to swerve away from quite above the boundary of its convergence range, which is shown by the vertical line, which is, by the way, of the order of the tau lepton mass. It is worthwhile to note also that the relative difference between the strong corrections to the proper expression for the R ratio and to its approximate form at the scale of the tau lepton mass is about 25–30% at the first two loop levels, then decreases to about 2% at the fourth order, but then rises back again to about 7% at the fifth order. As one can infer from this figure, and near the boundary of the convergence range, the full approximate form of the R ratio behaves somewhat better than the 5-loop one that can also be elucidated by the example shown on this page. So as discussed earlier, the pi-squared terms play a valuable role in the R ratio, and their ignorance, either complete or partial, may yield some misleading results. In particular, this issue is illustrated by this figure, which displays the two-loop time-like effective expansion function of the second order, which is shown here by solid curve, and its approximations, which are shown by dashed and dot-dashed curve, corresponding to various orders of its re-expansion at high energies. Specifically, the dashed curve shows the first term on the right-hand side of this equation, which is actually the only term which is retained in the two-loop approximation of the R ratio, whereas the dot-dashed curves additionally include the lowest order pi-squared terms, and the numerical labels indicate here the highest value of power of inverse logarithm retained on the right-hand side of this equation. Well, as one can infer from this figure, this re-expansion converges very slowly at low and moderate energies, and even at relatively high energies, the left-hand side of this equation considerably differs from the first term on its right-hand side. Specifically, at the energy as high as the QCD scale parameter times 20, which is at least of the order of several GeV, the first term on the right-hand side of this equation exceeds its left-hand side by more than 20%, and to securely achieve 10% accuracy at this energy scale, the inclusion of all the pi-squared terms up to the 7th order is required, in this re-expansion is required. And moreover, as one can infer from this figure, the convergence of the re-expansion is not uniform. Specifically, the inclusion of the 4th order correction makes the approximation even worse than the 1st order one. Then the 5th order is somewhat better, but the 6th order is worse. The 2nd order, 7th order makes the things better again, and so on and so forth.
Alexander, you're running out of time. Can you wrap up in 1-2 minutes, please?
Okay, I'll try. Thank you so much.
Thank you.
So to elucidate the impact of the higher order pi-squared terms submitted in the commonly employed approximation of the R ratio on the determination of the strong running coupling itself, it is worthwhile to note the following. This table presents the values of the strong running coupling and the QCD scale parameter at the first 5 loop levels extracted from the mean value of the base experimental data at 2 GeV. The first 2 lines are evaluated by making use of the proper expression for the R ratio, whereas the last 2 lines are evaluated by making use of its approximate form. As one can infer from this table, starting from the 3 loop level, the inclusion of the higher loop perturbative correction into the proper expression for the R ratio yields only a mild variation of the resulting values of the strong running coupling and the QCD scale parameter, thereby reflecting the aforementioned enhanced high loop stability of the proper R ratio. On the contrary, the use of an approximate form of the R ratio results in the values of the strong running coupling and the QCD scale parameter, which show no sign of convergence and swerve away from the values given above. It is worthwhile to say also a few words on the inclusion of the higher loop pi-squared term submitted in the approximated expression for the R ratio may produce a considerable effect even at high energies. Specifically, as one can infer from this figure, in the energy range planned for the future ILC experiments, the effect of inclusion of such terms appears to be either comparable to or even prevailing over the effect of inclusion of the next order perturbative correction to the R ratio. And additionally, in this energy range, the effect of inclusion of the pi-squared terms ignored in the 4-loop approximate expression for the R ratio and the resulting value of the strong coupling itself appears to be prevailing over the effect of inclusion of the 5-loop perturbative correction into this R ratio. All the relevant details can be found in these 2 papers. So in conclusion, let me summarize the basic results. The calculation of the R ratio of electron-positron annihilation into hadrons from the hadronic vacuum polarization function is studied within various methods. The renormalization group methods relations for the higher order hadronic vacuum polarization function perturbative expansion coefficients are obtained in the folded recurrent and unfolded explicit forms that can also be employed as an independent cross-check of the perturbative calculations, as well as in the studies of the renormalization scale setting. The explicit expression for the hadronic vacuum polarization function with properly eliminated dependence on the renormalization scale is obtained at an arbitrary loop level. The explicit expression for the perturbative spectral function is obtained at an arbitrary loop level that substantially facilitates the numerical calculation of the R ratio within the first method. The explicit expression for the R ratio, which properly accounts for all the effects due to continuation of the space-like perturbative results into the time-like domain, is obtained at an arbitrary loop level within the second method. It is shown that the first and the second methods yield the same result for the R ratio, and its truncated ring expansion at high energies is identical to the result of the third method of calculation. The explicit expression for the coefficients which embody the contributions of the pi-squared terms retained in a commonly employed approximation of the R ratio is derived at an arbitrary loop level. It is shown that the contribution of a given order to the proper expression for the R ratio appears to be redistributed over the higher order terms in its approximate form, thereby amplifying them. And eventually, this makes the loop convergence of a commonly employed approximation of the R ratio worse than that of its proper form, and increases the resulting uncertainty of the strong coupling and the QCD scale parameter associated with the disregarded higher loop perturbative corrections. It is shown that the validity range of the approximate form of the R ratio is strictly limited to this energy interval, and it converges very slowly when the energy approaches its boundary, which is of the order of the tau lepton mass. It is shown that the effective duty continuation of the space-like perturbative results into the time domain are only partially accounted for by the coefficients which embody the contributions of the retained pi-squared terms in the approximate form of the R ratio. And it is shown that the higher order pi-squared terms submitted in a commonly employed approximation of the R ratio can produce a considerable effect on the determination of the strong coupling and the QCD scale parameter from the experimental data on the R ratio of electron-positron annihilation into hadrons. And it is worthwhile to mention also that the detailed discussion of some of the presented results and many other related topics can be found in this monograph published a few years ago by Elsevier. Thank you very much.
Wonderful. Thank you very much, Alexander. Do we have questions? Yes, I see a hand. Zoom. Graz, do you want to go ahead? You're muted. Yeah, okay.
Yes. Concerning the results on your page 32, could you show them?
This one?
Yes. Now you show certain stability and the inclusion of more terms of alpha S. Strictly speaking, this is, do I understand correctly, alpha at space like S, 2GV?
Oh, yeah, sure. It is the standard running coupling, which is evaluated in the space-like region for at the 1, 2, 3, 4, and 5 loop levels.
And since your series behaves well for sufficiently high S, have you compared this high order expression of RS with experimentally available RE plus E minus?
Not yet, not yet.
Okay, that was my question. Thank you.
Thank you. Do we have other questions? Okay, if not, then let's thank Alexander again, and we reconvene at 4 o'clock sharp. Thank you.